has evolved to developing tasks where agents can actively sample data from an environment. AI agents are trained within a simulated graphics engine and explore it to find policies to solve useful tasks. A good example of this is visual navigation, where an agent needs to find a given target. It could be a sofa or a set of books on a shelf. And then any of these offline tasks could be ported onto this active or embodied domain. The work on this slide is an example where visual question answering is done using embodied agents. Here the agent moves around the house with a question in its mind: what color is the car? It learns to step out of the house and answer this question by saying it's orange after finding the car. Despite this embodied resurrection of computer vision tasks, there is still an aspect of human intelligence that all of these embodied AI tasks aren't being able to capture. And that is, we live in a multi-agent world where collaboration is an important aspect of our intelligence. Collaboration is prevalent in day-to-day activities of this multi-agent world of ours. It could be collaborating for safe driving, or teamwork for playing a sport, or the simple, not so simple, task of moving furniture. This is a glimpse of how our multi-agent world really looks like. And this is how the multi-agent virtual world looks like. The tasks are fairly intricate and communication is well studied, but the environments are two-dimensional or Gridworld-like in nature. As I mentioned earlier, the embodied tasks do look into photorealistic environments with the aim of transferring learning to the real world. But all the works before us present frameworks and approaches capable of addressing only single agent systems. And there is where we come in. We present the first simulation engine which has capabilities of handling more than one agent. It's a photorealistic simulation engine. Agents are visible to each other as cyan-colored cylinders. The top-down view on your left is only for illustration and is not available to the agents. What is available to the agents is their own first-person view, which is seen on the right. For this work, we stick to understanding collaboration between two agents. The framework and the approach I'll discuss is easily extendable to more than two agents, and we defer those aspects for future work. So, with our new multi-agent capable simulation framework, we can now deploy two agents with their own local views of this virtual world of theirs. We then went on to design a task so as to study the aspect of collaboration between these agents. One such task could be to now ask both these agents to navigate to a specific target, such as a television. This would be a simple extension of the single agent visual navigation task I discussed a little while earlier, the one with the sofa and the books. But jointly navigating to a target is something two of us can do fairly independently. We don't need to collaborate too much, do we? And hence, we add the component of lifting this TV, where the agents need to execute a pickup action jointly, that is, together at the same time. None of the agents alone have the capability to pick up this heavy TV alone, and hence have to collaborate with the other agent in the room. This is a quick run-through video of the task I just explained. With our multi-agent extension of AI to Thor, we instantiate two agents as cyan-colored cylinders. Agent 1 is marked in red and agent 2 is marked in green. I re-emphasize that the top-down view that you see on the left is only for illustration and is not available to the agents. What the agents are seeing is their respective first-person views marked as red and green boxes on the right. The white triangles that you see denote the viewing direction of each of these agents. So the red and green agents are tasked to first find the target television, which is marked in dotted yellow lines, and then coordinate a joint pickup. The red agent gets initialized close to the television and is quick to find it. The thick white line that you see in between on the top-down view is a wall with a door in. And what ends up happening is that the green agent gets stuck on the wrong side of the wall and keeps banging its head till it finally figures out a way through the wall to the other side. Notice how the TV is now lifted in the air after a successful pickup. And at the end of this episode, we are left with a feeling that if only there was a way for the red agent to signal to the green one that, hey, I'm over here and I can see the television. Or for them to coordinate this pickup together by doing a ready, steady pickup. If only there was a way of communicating this information, these agents would perhaps be able to do better. Which this form of communication is what I'll discuss just a little later. So the task has two components, navigating to the target and doing a collaborative pickup. The pickup is successful if it satisfies three conditions. First and the most obvious is that the agents need to be looking at the TV and must be close to it. Second is that these agents need to simultaneously execute a pickup action. And third, and this simultaneous pickup is because each of these agents isn't alone capable of lifting this TV. It's a heavy TV. And hence they need to execute this action together. The third condition is that the agents need to be on different sides of the TV so as to avoid toppling it over. The last two conditions of joint pickup and being on different sides of the TV are important conditions which impose a need for collaboration and also a need for communication. So here I present how the agent interacts with the environment and how this task presents a standard reinforcement learning framework. The agents operate over time where they have partial observation of the state, which we denote as OT. The agents learn to react to these observations by generating a distribution over the action space, which is the policy. This policy also incorporates a history of previous observations, which is denoted by HT-1. From this policy pi, actions are sampled for each of the two agents. This action tuple is then fed into the environment, which then produces the next observation, OT+1 for these agents. And this cycles around. More specifically, this is how the reward structure looks like for this reinforcement learning problem. We give each of the agents a +1 reward for performing a successful joint pickup, a -0.01 reward for every time step so as to reduce the length of the distance they travel. We impose a -0.1 reward for any failed pickup action. That is when either of the agents tried to pick it up alone or weren't close enough to the television. And we also impose a -0.02 penalty for banging into walls or in furniture. That way they learn how to navigate properly. We deploy an asynchronous advantage actor critic methodology to train this model. There is a value loss in terms of how accurate your estimation of the value of a state is, and there's a policy loss. Both these losses combined help train this network. The asynchronous nature helps deploy multiple instantiations of this environment and helps train this more efficiently. Now let me unpack for you the black box policy model that you saw on the previous slide. There is a convolutional neural network to process the image observation. The history that I talked about is captured using a hidden vector of an LSTM. Using the current observation and this history, the model generates the local belief of an agent, which we denote as H tilde. This is where we introduce a new module, the communication and belief refinement module. This module helps receive and send messages between agents. It also refines the belief H tilde by taking into account the communicated message from the other agent, and thus produces this refined belief H hat. This goes through another round of communication and belief propagation, belief refinement, to generate the final belief H of each of the agents. This final belief H is used to estimate the state value and policy of each of the agents. These estimates are functions of the parameters of this model and help train these parameters via an actor-critic loss. We also impose a cross-entropy loss as compared to a shortest path oracle agent, so as to make use of imitation learning to improve the efficiency of the model. This way we can train much faster as compared to pure reinforcement learning. Note that the agents are homogeneous in this case. They cannot be differentiated from one another. And hence, the parameters of the model are shared by both the agents. This again increases the efficiency of training. Note that the agents can communicate using two stages. We call them the talk stage and the reply stage of the network. Both of these are identical in structure, and so I'll discuss the structure in more details now of the particular talk stage. So let me unpack the first or the talk stage of the communication and belief refinement module. Overall, the objective of the module is to create a message signal for the other agent that we denote as m_send and generate a refined belief H hat. So these are the two outputs of this module. To do this, it utilizes two inputs. It uses a similar message from the other agent, that is m received, and the current belief H tilde. I utilize the superscript of T to denote that these variables are of the talk stage. We'll replace this with R for the reply stage soon. To generate the first output, that is mSend, we linearly combine two talk symbols, T1 and T2, by generating appropriate probability weights, PT1 and PT2. These weights are generated from the current belief H tilde. The module also receives a similar message from the other agent, which is marked as m received. This received message helps generate the second output of the module, that is the refined belief. More specifically, the received message m received is concatenated with the current belief H tilde and transformed to create the refined belief H hat. This completes the talk stage of communication. The reply stage is identical in structure. Just like the talk symbols T1 and T2, there are reply symbols R1 and R2. Similar to T1 and PT2, there is PR1 and PR2 on the right hand side. So these R1 and R2 reply symbols are combined using these inferred probability weights PR1 and PR2 to create the message mSend for the second stage of communication. I use the superscript R to denote the variables and messages for the reply stage. Hence, each agent learns to create a talk symbol or a talk message by combining two symbols T1 and T2, and it also learns to create a reply message by combining R1 and R2. The final belief H is utilized for the actor-critic head to train the model end to end. The actor part of this is used to train the imitation learning to calculate the cross entropy loss for the imitation learning as well. So we refer to this message-based communication as explicit communication. Between these agents, this sort of a message passing is what we'll refer to as explicit communication. Now, let's see how agents perform without and with this explicit communication. What's the difference in their performance? Here, I present the same setup that I showed before, which is without explicit communication. It's the same video as I showed earlier, the one where the green agent keeps banging its head on the wrong side of the wall and eventually learns to come on the other side. Note that without communication, it took the agents a total of 165 steps to complete the task. In this process, the agents failed to pick up the TV 6 times. So they executed these singular pickups on either side, which you are seeing as red and green dots over the trajectory. And as we know, eventually the green guy finds the door in the wall and comes on the other side to pick up. Now, let's see if we can improve this setup with explicit communication. With explicit communication, the agents complete the task almost twice as fast as compared to the agents without explicit communication. So the green agent does explore the environment by wandering about a little bit, but doesn't remain stuck on the other side for too long. Also, there are no unsuccessful pickups. So, explicit communication is indeed useful for the agents to collaborate. And as you see, it will lead to a joint pickup where the TV gets lifted in the air. But it's good that the explicit communication is working well. But what do these agents signal to each other which really helps them? We do present qualitative results as well as a detailed statistical interpretation of these messages in our paper. But for the purpose of this talk, I'll show the intuition and you can refer to the math in the paper. Let us start by seeing what agents signal in the talk stage of explicit communication. What I show in the plot below are visibility dots. They're a little hard to see, but I'll explain it. At a given step, a red dot means that the red agent can see the TV at this point. Similarly, a green dot on this plot shows that the green agent can see the television at this point. The x-axis is the time or steps in the episode. Note that the red agent was initialized close to the television, and hence it can see the TV quite early in the episode. The green guy could see the TV almost at the very end, marked by this small little dot, green dot at the end, at the 86th time step. And so this was because the green agent had to travel all the way from the other side to come to this side. Now what I show is the plot of PT1. That is the probability associated with the first talk symbol T1. I plot PT1 for both the red and the green agent. We find that, and statistically prove as well, that PT1 increases when the corresponding agent has a clear view of the TV. You'll see that by an increase in the red plot, whenever the agent starts seeing the red dots, and the green bar goes up only towards the end when the green agent starts to see the TV. Informally speaking, this helps signal to the other guy that, hey, I can see the TV here. We similarly analyze the messages of the second or the reply stage of explicit communication. Here we plot PR1, that is the probability weights associated with the first reply symbol R1. I plot PR1 for both the red and the green agents. The x-axis is again time or the number of steps of the episode. We find, and again statistically prove, that right before a joint pickup is about to happen, both the agents show a strong dip in the probability PR1s. Informally speaking, they try to indicate to each other that I'm all set for a pickup, let's do a pickup in the next round. And after this dip in probabilities, they execute a pickup which leads to the TV being lifted in the air. This completes the discussion on how these agents learn to communicate so as to provide useful signals to each other, much like how we humans would do for the same task of finding and lifting the TV. I'll show another such example where explicit communication helps improve the performance of these agents. Note that all the examples I'm showing are on environments which the agent hasn't seen during training. In this example, the agent wanders about for a little bit and reaches the target in 72 steps. They do attempt and fail picking up TV multiple times, 4 to be precise. And note that the TV is finally lifted in the air after the successful joint pickup happens, which happens after they fiddle around for a little bit. When the agents do communicate, they can solve the same task in much lesser steps. They solve it in just 17 steps, and the unsuccessful pickup actions are minimized to 0. We see similar trends in the explicit communication as we saw in the previous case. In the top plot, PT1 increases when the corresponding agent can see the TV, and in the bottom plot, both the PR1s show a strong dip right before they execute a joint pickup action. By being able to see each other, the agents get information about the location of the other agent and also its location with respect to the TV. Hence, visibility of the other agent serves as an implicit form of communication. So we experimented by making the agents invisible to each other. Note that we can still see the agents, they're visible to us, but invisible to each other. Otherwise, we would not know where they are. Here they neither can talk to each other nor can see each other. So now by taking away implicit in addition to explicit communication, we see a significant increase in the time it takes to complete the episode and also an increase in the number of unsuccessful pickups. It keeps wandering about the TV trying to coordinate a pickup action. We now quantify the effect of communication using these results. On the x-axis is the number of training episodes. On the left, we show successful episodes, a percentage of successful episodes. In the center is how many unsuccessful pickups did I have per episode. And on the right, we have missed pickups. Those are the opportunities where a joint successful pickup was possible, but the agents decided not to do a pickup. The red bar is with no communication at all. The green is with explicit communication. Orange is with implicit only. And blue performs the best, which is with both forms of communication. All the experiments, and whether it is qualitative or quantitative that I showed to you till now, were all on unseen environments. That is, these environments weren't seen during training. Note that this is not a standard reinforcement learning approach. Most of the reinforcement learning papers show training and testing on the same environments, whereas we show a strong generalization across from seen environments to unseen environments. This experiment is an attempt to quantify how difficult collaborative tasks are in the visual domain as compared to the Gridworld domain, the 2D environments that I showed to you before. So we translate the visual world to an analogous grid world where information about each grid cell is available in a much cleaner form. That is, no computer vision is needed, neither deployed. So this is how the analogous grid world to our task would look like. And when we trained agents to do the same task in this analogous grid world, we found that the agents perform much better, which means that on all the metrics, especially the accuracy, which shows a difference of 20% in between the visual world and the grid world, providing additional clean information such as depth or depth maps does improve the performance of the visual agents. So with this quantitative study, we conclude that the environments requiring visual processing are much different and more difficult than simple 2D environments. Hence, collaborative visual agents present a new direction and pasture for interesting future research. To summarize, we introduced the first multi-agent simulation framework for photorealistic environments. We introduce this find and lift task, which is inherently collaborative in nature. We propose a reinforcement learning framework where, with a partially observed state, policy function, and environment interaction, we can train agents within this setup. In addition to an A3C RL solver, we also make use of imitation learning so as to increase the efficiency or the sample efficiency of our model. We go into details of the policy network, which is a two-body network where the parameters are shared across the homogeneous agents. We devise modular communicating blocks, which also help refine the belief of the environment. In addition to showing improvement in performance, we statistically and qualitatively interpret these messages between the agents. We then show results on different metrics and also show a strong generalization. Finally, we establish how collaboration in visual environments is much more difficult than collaboration in 2D simplistic environments. With that, I conclude, and I'm open to questions.